Welcome to the session on solutions to the Navier-Stokes equation. We will be taking up simple cases, and in this particular session we will be taking up the cylindrical coordinate system. In the previous session we have done the rectangular coordinate system, and this is as part of the NPTEL MOOC on transport phenomena in materials. So, in this session we will be first looking at a simple interesting case of fluid statics, whereby we will be conscious of the pressure term also being varied as a function of the spatial coordinates, and then we will look at how the three different components of velocity in the cylindrical coordinate system, namely the radial component, the axial component and the theta component, can be solved for in three separate problems. So, we will be taking up unidirectional flow in this session. So, we will take up only one component at a time in each problem. So, here is a depiction of how the components are looking like. The what we refer to by axial component is this, which is along the z direction, which is along the axis of the cylinder, and the radial component is here. So, it goes from the center towards the periphery of the cylinder, and along the theta direction is the theta component. Okay. And we have problems in which one or more of these components will be present, and we will take up problems one after other to see how the equations can be solved for. As you can see that the theta component is pegged at the end of the r vector, and as a function of theta, which I am showing here, the location of the vector v theta would be changing. So, this actually means that in the cylindrical coordinate system, the Navier-Stokes equation will have terms that are in addition to what normally are expected from the rectangular coordinate system, and we must be conscious of those terms while solving the equations. So, here are the equations that we have shown in the earlier session on how the Navier-Stokes equation would look like for different components of the cylindrical coordinate system. So, I was drawing your attention to essentially terms like this. For the r component, you have this term which is coming in, and you do have for theta component also some term that is coming in. And in addition, the Laplacian also would have a special appearance where you have got 1 by r going in, and here also there is an additional term. So, it is not directly substituting x y z with r theta z, but we need to watch out how the coordinate system transformations are being used. So, pay attention to these terms that are being highlighted, so that we can notice that the terms are looking a little different in the cylindrical coordinate system. Okay. So, we will take problems that will use these equations one at a time. So, first problem is about a statics problem, namely the situation where we are only looking at how the pressure would change as a function of distance. So, here is a situation where you have a container of liquid which is made to rotate about its own axis. So, this is the rotation that is happening, and because of this we expect normally that the liquid will be pushed away from the center. So, it would climb up the wall a little bit, and it would take the free surface would take a shape. Now, we are interested in determining this shape just from the statistics. So, from the statics what we know that this shape is given by the condition that because it is a free surface. So, you say that this is a free surface. So, it means that atmospheric pressure is what is acting on the liquid at that location. So, which we determine here as a condition. So, P is equal to P naught is the atmospheric pressure, and if we choose omega, then depending on the magnitude the Z naught also would change. So, we indicate that in the problem here Z naught. So, we want to assume that there is no theta variation, it is an axisymmetric problem. So, we now have a situation where pressure is a function of r and z, and we want to determine that. So, the equations are here. Now, these equations are going to be very trivial because we do not have velocity components except in the theta direction. So, because r velocity is not there, so wherever u r is there, those components will be all going off. So, I strike off all of those, and we also know that we have chosen the axisymmetric situation. So, we strike that off also, and there is no body force term along the radial direction. So, which means that you have got only two terms which we have indicated here as the first equation, which will give you the radial variation of the pressure. So, similarly for theta, we say that it is a steady state and there is no UR and there is no UZ, and here also is no UR, and axisymmetry, and we say that again from the axisymmetry, and UR is not there, and there is no Z variation of velocity in the theta direction. So, it basically leaves us only one term, and we also want to say that there is no axisymmetry also makes the P not varying along theta, and there is no body force acting in the theta direction. So, we have a very simple equation that has only one term. So, that comes here. Now, the boundary condition is such that the linear velocity at the end of the container is given by r omega. So, that if you plug in, then you see that the equation is satisfied. So, V theta can be taken as r omega, which we can substitute and see that it satisfies. So, in the case of z direction also, the velocities are actually not there, and so you have those terms going away, and you see that this must be the body force, which is basically the gravity term, and this must be the pressure variation because of the z direction having different heights of the liquid as you go along the r. Okay. So, you have this equation. So, you now have these two equations which are need to be solved, so that we can get P as a function of r and z, and we substitute V theta expression into this equation. So, we do that, and so then we arrive at these two equations which need to be solved simultaneously. So, there will be some integration constants that we are actually determining from the fact that atmospheric pressure P naught is there on the surface of the liquid. So, which when we plug in, then we can clearly see from here itself that the first integration will give you r square by 2. So, there is a this term, and the second integration will give rho g z, that is this term, and the remaining ones are coming from the integration constants. So, which means that the pressure variation in this particular situation where the liquid is being turned. So, this pressure variation is given by this particular functional form, and therefore, wherever P is equal to P naught will give you the curve, this particular curve. So, the free surface is then given by a functional form like this. So, Z is going as r square. So, Z going as r square would imply that we have a parabola, which means that when we rotate a container of liquid about its own axis at a velocity, angular velocity omega, then depending on the magnitude of omega, the parabola will be deeper at higher magnitudes, and this kind of a situation can be used to make actually parabolic mirrors. So, we see that the idea of a parabolic shape has come out only from the statics problem when there are no velocity components at all, and by looking at the equations in the Navier-Stokes equation for the cylindrical coordinate system. So, this is interesting, and we are actually now seeing that the pressure variation can also be derived from these equations. So, now let us look at the three components. So, we will take one component at a time. So, the radial component is being taken. So, radial velocity component is UR, and the continuity equation needs to be satisfied, and also the Navier-Stokes equation. So, we saw that if you look at only the continuity equation, we already can guess what kind of forms are allowed. Okay. So, we see that if it is a unidirectional flow, so then this functional form should give us that UR should go as a function of 1 by R, so that it can satisfy the continuity equation. And when we plug in this into the Navier-Stokes equation and look at situations where it is a simple situation like steady state, and you do not have a u theta, and you do not have a uz, okay, and there is no theta variation, and there is no u theta, and there is no z variation. So, you could already see that here again you could see that this is already satisfying. So, this would go off, but what you could see that these terms would still survive. So, which means that even if you want to drop this term saying that there is no body force along the r direction, you can see that there must be a pressure variation as a function of r if you want to use a simple form of radial velocity like this. So, this can be immediately plugged in and you can derive it. So, I would leave that as a homework for you, but it just shows you that when you actually plug in the functional forms for the unidirectional velocities that you can conclude from continuity equation, then you may have actually pressure variations also to be taken into account as we go along. So, we now will look at the second component of the velocity in the cylindrical coordinate system, that is the axial flow. Okay. So, that is uz. Okay. So, along the z direction. Now, for that we choose a problem that is very standard that has to be learnt by all students who are studying this particular subject, namely flow through a pipe. So, you have a pipe and liquid is actually going through that, and the reason why it is able to go through that is because either there is a body force that is acting along the length of the pipe. So, in situations where the pipe is vertically kept, because of the gravity the liquid will flow through that. That is one way. Another way is actually there is a pressure gradient along the pipe. So, when you have a high pressure here and when you have a low pressure there, so because of the negative slope of pressure, then you have basically velocities in the positive z direction. So, that is what is indicated here in terms of pH and PL. Okay. So, you have got these two situations, and so the flow is due to one of the two terms or a combination of the both. Okay. So, Fz is a body force term, that is G, and 1 by rho delta P by L is basically the term corresponding to the pressure drop. So, because of one of these two reasons, the flow is happening along the axial direction, that is along the z direction in this particular tube. Now, the inner walls of the tube are assumed to be rigid, smooth and so on, and so the boundary conditions that are applicable are that the velocity at the inner wall is 0. This is from the no slip condition, and we also want to say that along the diameter there is a symmetry, which would mean that the velocity profile should have a finite value at the r is equal to 0, or you have a slope that is 0. So, both would actually mean the same thing when we are solving the equation, but we need to use one of those two principles at the center, that is either the symmetry or the velocity being finite. So, what is the equation that we need to write for this particular problem? So, we have basically the equation, Navier-Stokes equation for the z component of the velocity. So, that is what we are going to write. So, we have already written the equation, which means that we have already made these three assumptions, and more than that we are also going to make assumptions. So, we are going to strike off the first term because of the assumption 4 steady state, and we are saying it is a unidirectional velocity along z. So, there is no u r. So, and then there is no u theta also, and so that would be gone. Okay. And we say that the velocity variation is only along r. So, variation along theta direction is being dropped. So, that would be assumption 6. Along the z direction we say that it is a fully developed flow. So, we want to strike that off, saying that it is because of the condition 7 that these two will be gone. So, then we also want to say that there is an axisymmetry, of course that would also make this go away. So, one of the assumptions will actually that's taken care. The constant body force term, which means that this is actually constant, that is only to make the integration easier for us. Okay, otherwise there is no need for that to be constant. So, you now have the Navier-Stokes equation having only two terms, and that would look like that. So, when we now integrate, so take this term to the other side, so you get a minus sign, and then you integrate once. So, then you can get the r coming in, and then the integration constant is C1. Okay, and when you integrate once more, you can see that this would actually give you a log term. So, that would be a problem, because at r is equal to 0, log r would actually blow up, and we want the velocity at the axis center to be finite. So, which means that we do not want C1 to be present, because C1 by r actually will give you a problem when we integrate the next step. Another way to say it is, because of the symmetry, we want that the velocity profile will be having symmetry along the diameter. So, which means that at r is equal to 0, the slope of the velocity profile in the r direction will be 0. So, which means that again this term should be 0, because if this is 0 at r is equal to 0, then this must also be 0. Okay. So, either way we are arriving at the conclusion that C1 is 0. So, we substitute that and integrate once more. So, we get a functional form that looks like this. So, this is basically the solution of the z component or the axial velocity component in cylindrical coordinate system for the list of assumptions that we have mentioned. And when we apply the boundary condition that at the inner wall of this pipe you have 0 velocity because of no slip, then we can determine what is the C2. So, the C2 is then determined here, and when you substitute you get the functional form of the velocity, which is appearing to be like a parabola, because you already see that there is a r square variation that is coming in. And what would be the maximum velocity? When you substitute r is equal to 0, you get the maximum velocity. So, which means that let us say you have got only one of the variations. So, because of only pressure drop. So, if only pressure drop is present, then the maximum velocity is then given by 1 by 4 mu delta p by L into r square. And you could also write, for example, as rho g r square by 4 mu. So, the terms can be added if both of them are acting simultaneously. Now, when we want to look at the velocity profile, just by normalizing the velocity so that we only look at the shape of the velocity profile, then it would come out on the right hand side with only a profile form, which means the scaled radius if you use, then it just goes as 1 by 1 minus r square. Okay. So, which basically means it is a parabola, and this actually is already encountered in a similar problem in the rectangular coordinate system as well. Okay. So, this functional form is very important because this will be then used in many situations as we go along. Now, when we plot this parabola, it would look like here. So, this is the plot we are trying to show. So, which means that in the tube at the center is the maximum velocity, and at the walls it is 0 velocity, and the slope at the center will be 0, and the parabolic is the nature of the velocity as a function of r in the tube. Now, you can already see that from the Newton's law, slope of the velocity profile should actually indicate what kind of shear stress is present at that particular location. So, you can already see that the slope is 0 here, which means that the shear stress is 0, and then the slope is actually here. So, it appears as if the slope is changing the sign when you go from here to here, but please remember that this is actually a cylindrical case. So, this is r and this is also r. Okay. So, because of that the slope actually is having the same sign on both sides, and that is negative. The reason why it is negative is evident when you actually mathematically show here and then plug in. So, you can actually see that from the expression for tau z r going as dou u z by dou r for unidirectional component. So, you can already see that it comes as minus r, and from the convention that we have already seen, we can actually apply that. So, the layer at higher r, and higher r is basically the wall, okay, on the layer at lower r, and that is the liquid. So, the stress that is acted upon by the layer at higher r on the layer at lower r, that is the stress acted upon by the wall on the liquid. If it is actually along the positive z direction, then the stress is positive, but actually as we can see here, it is actually trying to stop the velocity from taking a magnitude at the wall, and therefore, the stress is actually acted upon in this direction, that is opposite to the positive z, that is in the negative z. So, therefore, the stress has to be negative. So, that is how the convention actually is also coming out neatly even in the cylindrical coordinate system from what we have written earlier. So, mathematically what is shown, if you plot, it actually also makes sense with respect to the functional form that we have given. And what is the average velocity? This is very important because we want to determine the flow rates through pipes and junctions of pipes, etc. So, the average velocity is always generally over the area through which the flow is taking place. So, you know that the area element is generally given in the cylindrical coordinate system as r dr d theta, and so you just take that area element and integrate over the entire circular domain, and so which means that the theta is 0 to 2 pi and the domain is defined by this, and in the numerator you actually have a functional form from z. So, that also if you substitute, then you do have expression coming a little more elaborate. So, we go through that algebra, it is quite straightforward, you can just substitute and integrate, it is just integration of only r and r cube. So, if you substitute, you basically then arrive at this conclusion that the average velocity is half of the maximum velocity. So, now this is interesting because in the rectangular case where we had the parabolic flow variation, the average was coming to be 2/3 of the maximum velocity, but in the cylindrical case the average is coming to be half of the maximum. So, the reason of course is because the domain is in a cylindrical coordinate system like this. So, the r that is going in is actually making this integration little different from the rectangular case. Okay, so, we then can use this to flip between the two quantities that we want to know. So, very often maximum velocity is not given, average is given, and then we can actually then determine the maximum velocity and then use that as a scaling factor for the functional form, and then therefore get also the velocity variation as a function of r. Now, often the volumetric flow rate is actually asked because we can actually collect the liquid that is coming through the pipe for a given duration, and then from there determine what is the V dot. So, how is the V dot related to the average velocity? It is basically average velocity into the area through which the flow is happening, that is the V dot, and if you substitute, it comes out to be this expression. So, this is something that we need to use, and if you multiply the volumetric flow rate with the density, then you actually have the mass flow rate, and that is also straightforward. You can use it here, the average velocity into the area pi r square into rho. So, that would be giving the mass flow rate. So, mass flow rate has a name. So, Hagen-Poiseuille equation. So, this equation actually is quite popular, and if you plug in the numbers and get the average velocity, then that can be used to determine the flow variation. So, we now move to the axial flow, but in a small deviation. We earlier had a pipe with the circular cross section, but in this situation we want to have annular cross section. So, we have our domain little different. So, the domain is looking like an annulus. So, the domain is defined in this manner. So, if you have Kr as the inner radius, so this is the domain, okay, and the liquid is actually going in the annular region like this and in the axial direction. So, it is still in the axial direction only. So, boundary conditions will be as follows. So, the liquid is actually flowing because the inner shaft is being pulled out at a velocity v naught, and because the liquid would get stuck to the both the walls because of no slip condition. So, there will be a shearing of the liquid. So, velocity gradients are being set up. So, the boundary condition on the upper wall, this is act r is this. So, that is giving you actual velocity to be 0 because the outer container is stationary, and at r going to Kr, the velocity is given by V naught because the situation is that of a moving wall. So, both of them are actually no slip conditions only. So, the flow is happening not because of any driving force, but only because of the moving walls. So, if this is a simple situation, how would we go about arriving at the solution? So, that is quite straightforward. We basically have the same equation that is written, and we take the steady state assumption and unidirectional velocity along z. So, the theta is not there, and theta u theta is not there, and then u r is not there, okay, and then velocity variation is only along r. So, variation along theta should be knocked off, and along the z direction also to be knocked off, and axis symmetry also implies that this is gone, and the fully developed flow would actually want you to drop this term, and then these are not there. Okay, so 0, because we say that the flow is because of only the boundary conditions and not because of anything else. So we just drop this, so which leaves us only with these terms, and so that term we basically write it, and this is now the trivialized form of Navier-Stokes equation for z component, and when we integrate twice, then we get the logarithmic term. Now in this situation we are not actually dropping the logarithmic term, because there is no domain is actually not containing r goes to 0, so we do not have a problem. Okay, so we have this as a functional form. So when we integrate twice, so we get 1 by r, and then second time we get logarithm of r, and the boundary conditions will be used to determine the values of C1 and C2. So they are written here. So you just have to substitute, and then if you subtract the second equation from the first equation, you get the value of C1, and you substitute the value of C1, then you get the value of C2. So once you get, then you can write the uz as a function of r, and then simplify it, and then it looks like this. Okay. Now here can this equation be used for pipe flow? That is situation where here we say that inner and outer, so r inner and r outer. So r inner actually is k into r, and r outer is r. So if k tends to 0, what does it imply? It means that you are actually making the annular region look like a cylinder pipe flow problem that we have come across earlier. So can we use that equation for such a problem? So evidently not, because we actually kept the logarithmic term with us when we did this integration, and in the process actually now the solution has logarithm. So when you actually want to reduce the domain, then at the axis you have a problem. So one should not blindly use this in such a situation. Okay, so that is what I wanted to alert, saying that when we use a boundary condition while arriving at the equation, then anything that actually violates that particular condition should be watched out for. So the boundary condition in this case is that at r tends to 0 there is no problem, and but then when you extend the domain, then there will be a problem if you actually apply it for a cylindrical pipe flow case. So we should not use it. So the solution for annular case should be used only for annular axial flow. Okay. Now we can actually see under what circumstances this particular flow form can be approximated to a planar case. So what we do is this annular region. So what we try to do is that this distance alone we want to express and say that it goes, okay, so going from here all the way from 0 to delta. Okay, so we define in such a way that delta is nothing but the distance here, okay, and y is going from 0 to delta. So from either outer surface to inner surface or inner surface to outer surface. So we define that way. So which means that in the way we have defined r is equal to capital R minus y would mean that it is going from outer to inner, okay, and that is the distance that we are taking up. So what we do is we just substitute these two forms into the solution that we obtained, and then you will see that the scaled form used by V naught is coming out to be this. Okay. Now here in situations where the delta is small, so if delta is small, you know that then delta by r as well as y by r are very small. So if they are very small, what happens is that logarithm of 1 minus x can be approximated to minus x, and so if you do that for both numerator and denominator, then you have a situation that is simulating what happens when k is tending towards 1. Okay, of course you should not plug in k is equal to 1 because you have a problem that will come in the denominator, but in the limit you can actually see that it comes to be basically a ratio of y and delta. So what it implies is that when the delta is very small, so this is the same as saying that k tends towards 1. This actually is the same as the gap is very small compared to the dia. So under these situations we can see that the velocity profile can be given by a linear relationship, but we already know this solution. We already know that this solution is applicable for a problem where here is what we have originally looked at. Okay. So, this is for a problem that we have already come across. So, which means that the axial flow problem can also be reduced to a planar problem in situations where the gap is very small compared to the diameter of the cylinder. So, some problems you do not have to actually use a cylindrical coordinate system just because the domain is actually having a cylinder in it. We can actually approximate it to be planar problems, but remember that it is applicable only when these kind of limits are applicable. So, only in extreme situations such approximations can be made. Now, we take the last component of the velocity in the cylindrical coordinate system, namely the u theta. Okay. Now, u theta in this particular problem is actually called as the solution for the co-ed flow. So, the situation is as follows. So, you have got two cylinders that are rotating, and the inner and outer velocities are different. Okay. And the radii are also different, Ra and Ro. So, which means that Ri minus Ro will be the annular region, and the velocity is now not axial in the annular region, but actually along the theta direction. So, what we have drawn is basically something like this, and so the two cylinders are rotating about the center axis, and their velocities are different. So, therefore, the liquid between these two cylinders is getting sheared. Okay. So, this kind of a problem can now be looked at. So, the flow is actually happening not because of any term, we do not want to consider any body force, any driving force there, and we want to say that this flow is happening only because of omega I and omega O, that is inner and outer angular velocities. So, the boundary conditions are straightforward, the no slip conditions are applicable. So, for the outer wall, the linear velocity u theta is given by Ro omega O, for the inner wall it is given by Ra omega I. So, these are the boundary conditions at inner and outer walls. So, the equation that we need to solve is here. So, we already wrote the equation for a Newtonian fluid, for an incompressible fluid which also has constant properties. So, that equation is already assuming the first three assumptions. So, we assume that the steady state is applicable, and then unidirectional velocity along theta. So, which means that u r is not present and u z is not present, and we want to also say that there is a velocity variation only along r. So, along the z direction it is not there, and we also want to say that there is an axisymmetry. So, the theta variation is also being dropped. Okay. So, okay, and this is also because of axisymmetry. Okay. And we also want to say that these terms are constant and they are 0. So, because we say that the flow is not due to any of those terms, it is only because of the boundary conditions. So, which means that we have got a very simple equation that is coming in here. So, that equation is written here, and we then integrate. So, when we integrate twice, then we get a functional form which goes as r plus 1 by r. Okay. So, there are two integration constants C1 and C2, and when we substitute the boundary conditions we can determine. So, the inner wall boundary and outer wall boundary conditions are listed here. So, what we do is that the first one, if you multiply with Ro, the second equation if you multiply with Ri, and then if you subtract, then you could see that you would eliminate the terms and then start to see the solutions. So, the solution for C1 and C2 are available, and then when you plug in, you have got the velocity in the theta direction. So, though there are number of terms, you can see that the functional form is essentially r and 1 by r that is coming in. Okay. Now, we want to look at under what circumstances such a solution can be simplified. So, again like we have done just now, what happens if the gap between the inner and outer walls is very small compared to the diameter of the inner cylinder or outer cylinder for that matter. So, we want to make the simplification like this. First of all, we want to consider that only one of the walls is actually moving, that is just to make it simpler. So, omega I is taken as 0, and the outer wall we want to determine the linear velocity and we want to give a symbol. So, u naught. Okay. So Rho omega O is u naught. Okay. Now the annular distance is being defined in the same way like we have done earlier. So earlier it was like Ri and Ro. So we want to define the distance as follows. So we want to now say that this is capital R, and from here onwards it is basically y, and the total distance here is delta. So when we want to define that way, then we say that for the case, we want to do this for the case where delta is very small. Okay. And when delta is very small, it also implies that Ri, Ro are both very close to R. Okay. And which also means that Ri plus Ro is very close to 2R and so on. Okay. So we make those simplifications and look at how the V theta is varying. So we just straight away plug in and then get this equation and then simplify this. So in the denominator, Ri square minus Ro square, you write it as Ri plus Ro into Ri minus Ro. So then they will be looking like 2R into delta. So that we write, and then the equation would look like that. Okay. Now in the limit that Ri and Ro are very similar to each other, then we see that this can actually go as a unity. So it tends to unity. So which means that the V theta by u naught goes as y by delta. So again we have come to the same equation as we have done earlier. So which means that in a situation where actually this is what is happening, then you can look at the domain and imagine that this domain is in a situation like this, and so flow would be like this, and which means that a situation where you have got a very small gap between the two cylinders compared to the diameter of either inner or the outer cylinder, then the cylindrical problem can be reduced to a planar problem. Okay. So for small domains this is applicable. So you can already see from the solution that these simplifications are possible. Okay. So it's not necessary that you have to solve problems in cylindrical geometry by using the cylindrical equations. Under suitable situations you can actually reduce the complexity. So at this moment we just close this session, and in the course website you have got notes and practice problems where some numerical problems also will be available for you to plug in and see how these equations can be applied.